a small oil drop of mass hanging at rest between the plates. Common potential difference or potential difference. Charge on the drop is. Understand the problem? There is a charge, oil drop with charge Q. There is weight is mg. But this is hanging means this charge should experience upward electric field, electric force. Electric force is Q into E and E is V by D. So this should be equal to this to be at rest, isn't it? Therefore, mg equal to Q V by D. Now what we want is charge on the oil drop. Charge is here. M is minus 6, G is 10, D is distance between the plates, milli, minus 3 by voltage. Voltage is 500. So this is charge. Students, try to avoid writing one more step, okay? Which is that one more step here? I'm not writing, but you should not write. Charge equal to mgd by V. This is a simple equation, right? After rearranging this, you will get this. Don't write this because you are avoiding this step means you are saving some 5 seconds. You are saving such 5 seconds means it's a good attitude towards entrance exams. Good. So if equation is very simple, try to avoid as many steps as possible and proceed. See, 10 by 5 is 2. 2 is there in every option. So we have to check the power. Minus 6, minus 3 is minus 9. This minus 2 goes to numerator, minus 11. So 2 10 to the power of minus 11. Now, let me explain why this is equal to this. Why this is equal to this. If there is charge and that oil drop is at rest means this mg should be balanced by upward force. That upward force is due to electric field. So force equal to charge into electric field. So this is the upward force. And electric field is equal to minus dV by dx. Negative potential gradient, second chapter, relation between electric field and potential. So same equation can be modified to E equal to potential difference by distance between the plates. Minus dV is potential difference. Distance between the plates is x. So in place of E, we can write V by x or V by D, distance. So that is why QE is the force, electric force. And in place of E, V by D. So I equated this with this downward force. So mg equal to Q potential difference by D. Students, to get such shortcut methods in most of the multiple choice questions in your 11th and 12th standard, subscribe the channel and get updates on all the latest videos. Two metal spheres are given a charge respectively. They are then connected by a wire. The final charge on the first sphere is charge on the first sphere. This is sphere, second sphere, radius of first is 10 power minus 2 meter, radius of second is 2 10 power minus 2 meter. Okay. Charge on the first is 15 millicoulomb, 15 millicoulomb, and second is 45 millicoulomb. Now they are connected by a wire. They are connected by a wire. They are asking final charge on the first sphere. Charge on this plus charge on this is the total charge. So let us start with total charge equal to Q1 plus Q2. Total charge is this plus this, 60 millicoulomb, 10 to the power of minus 3. And charge is capacitance of the arrangement into C, sorry, into V. So this is common potential difference. Sphere has a capacity to hold charge. Now it's an extra point. Capacitance of a sphere. Capacitance of a sphere is given by 4 pi epsilon naught r. Okay. Constant into r. It depends on the radius. See, radius of first, radius of second. If these two are connected by a wire means they are like in parallel. Capacitors in parallel means C1 plus C2. Total capacitance. C1 plus C2. Fine. So this C is C1 plus C2. But C is constant R. Therefore C1 plus C2 is 4 pi epsilon naught into R1 plus R2. So this is actually 4 pi epsilon naught R1 plus R2. Now common potential difference equal to 60 10 to the power of minus 3 by C. C is 4 pi epsilon naught R1 plus R2. See, 4 pi epsilon naught R1 plus R2. Now it is 60 milli by R1 plus R2 is sum of these two. That is 1 plus 2, 3. 3 10 to the power of minus 2. 4 pi epsilon naught, 1 by 4 pi epsilon naught is 9 10 to the power of 9. Observe, 3, 1, 3, 2, 20. So common potential is 20 to 9 to 18. 18, 10 to the power of 0, minus 3, 10 to the power of minus 2, minus 2 get cancels, 10 to the power of 9. Okay. Now what we want is the final charge on the first sphere. Final charge on the first sphere means Q equal to CV. C1 V1. C1 is 4 pi epsilon naught into R1 into common potential is 18 10 to the power of 9 equals 1 by 4 pi epsilon naught is 1 by 9 10 to the power of 9. Okay. And then R1, radius of first one is 10 power minus 2. Common potential is 18 10 to the power of 9. 10 power 9, 10 power 9, 18 by 9 is 2, 2 10 to the power of minus 2. So final answer is 2 10 to the power of minus 2 coulomb. 2. It is here. It is in terms of 10 power minus 3. True. Give 1 0 to this. It becomes 20 10 to the power of minus 3 coulomb. So it is 20 10 to the power of minus 3 coulomb. Okay. So here few concepts are involved. Capacitance of a spherical conductor is this. Second concept. If those two conductors are connected by a wire, then common potential difference is found out by Q equal to Q1 plus Q2. Q1 plus Q2 is mentioned. Total charge is effective capacitance into common potential. Then third, how to find charge on each conductor? Charge on each conductor is Q equal to CV. So this is the procedure. Okay. Two concentric spheres of radii R and R have positive charges Q1 and Q2 with equal surface charge densities. Fine. What is the electric potential? Please understand what's the electric potential at the common center. This is first sphere, second sphere, common potential at the center is this. You hardly required 5 seconds after reading this problem. Why this is the option means there is a charged sphere of radius R. Electric field at any point on the surface is sigma by epsilon naught. Okay, electric field. And electric potential at any point on the surface is sigma epsilon naught into R. R is radius. R is radius. See, potential is sigma by epsilon naught into R. Because of outer surface, sigma by epsilon naught R, plus because of inner, sigma by epsilon naught into small letter r. So total potential is V1 plus V2. So common factor sigma by epsilon naught R plus R. Students, next time when you come across conductor and potential in terms of charge density, directly use this equation. Okay, charge density by epsilon naught. This is from first chapter, Gauss theorem, and this is R. So sigma by epsilon naught R plus R. Two capacitors are connected to these two. If they are connected by a wire, what is the common potential of the capacitor? This is first capacitor. This is second capacitor. They are connected means they are in parallel. What is the common potential of the capacitors? Common potential of the capacitors means start from total charge. Total charge equal to Q1 plus Q2, but Q equal to CV, isn't it? So Q1 is C1 V1, Q1 is C1 V1, Q2 is C2 V2. Please don't write these steps here. Q1 is C1 V1. See here, C1 V1, product of these two is 2000 pico. 2000 pico is 10 power minus 12 plus C2 V2, product of these two, 2000 is 2000 pico, 10 to the power of minus 12, and total charge is equivalent capacitors in parallel into common potential difference. So what we want is this common potential difference. Okay, this common potential difference. Therefore, common potential difference equal to this divided by Cp. This plus this is 4, 10 to the power of minus 9 by Cp. C1 plus C2. C1 plus C2. 20 pico, 10 pico, 30 pico. 30 pico, 10 to the power of minus 12. 4 by 3. 4 by 3 is 1.3 something. 1.3 is here. When capacitors are shorted means it should be like this. And there are two cases. Let me tell you those two cases. If two capacitors are shorted like this, okay, with positive connected to positive, negative to negative. In this case, you have to take total charge equal to Q1 plus Q2. And the procedure is as usual. Second case, if two capacitors are connected like this, with plus connected to minus and minus connected to plus. In this case, total charge is Q1 minus Q2 or Q1 difference Q2. Okay. Here, polarity of charges is not mentioned. They are connected by wire. That's all they have mentioned. Connected by wire means take it as this case and try to solve. So it is 133 volt. Charge in this plus charge in this is Q1 plus Q2. These two are connected in parallel, then effective capacitance is Cp. Charge in this is this. This charge is charge in the effective capacitance. Effective capacitance is Cv. Cp, they are parallel, common potential Cv. So this is how you should solve. What is the electric potential at a distance of 9 cm from 3 nanocoulomb? Direct question, isn't it? So some charge, some point, potential. Charge is 3 nano, distance is 9 cm. So potential is constant Q by R. Constant Q by R. Constant is 9 10 to the power of 9. Charge 3 nano, minus 9 by distance 9 centi. 9 get cancels, 3, this get cancels, 3, there is 10 power 2, so it is 300 volt.